all of this year's sponsors for their continued support. This afternoon, we're delighted to welcome Sharon Keane, Training and Development Manager with Zinworks, based in Athlone. Sharon is a software engineer with a passion for DevOps, software testing, and continuous integration. Sharon works primarily in the telecommunications domain, focused in 5G, cloud-native applications for network slicing and VNF deployment and testing. Today, Sharon will be discussing the technology and new concepts that are driving the 5th generation of wireless communication and how it affects the everyday end users. 5G is making the world an even smaller, and we're seeing the drive towards Industry 4.0, the 4th industrial revolution, which will drive lots of new business opportunities and innovation. So once again, and keep those questions coming in on the Q&A, and Sharon, it's over to you.
Thanks a million, Seamus. I'll just get my screen share here. Great, so I hope you guys can all see my screen. So thanks, Seamus, and welcome everybody here today. We're going to have a look through 5G and getting a speedy overview of some of those buzzwords and concepts we hear every day when we do talk about 5G. So 5G is just faster downloading of movies to your phone and higher quality videos and online gaming, right? I suppose if it was that much, we wouldn't have a talk here today. Well, if we look at some of the concepts and capabilities and what if we look at some of the 5G concepts and capabilities and what the fundamental network changes are, we will get to know a little bit more about what 5G is. So the first cars seems like a strange place to start with an image like this, but the first cars were built in 1880. But within 40 years, people started imagining self-driving cars. But the autonomous vehicles were never realized outside of movies like Knight Rider and Herbie. So if we look at today's companies like BMW, Jaguar Land Rover, Tesla, Google, and many others, they're all working on their own self-driving prototypes. And I'm not sure how many people got to catch Ken Power this morning, but there was an amazing talk and he went into some of the advances there around the autonomous vehicle and the actual software within the cars and the machine learning. But why today? What's making this a reality today? When will we be able to feel like 00 agents? This is my big question, and have our car speeding up to us at the touch of our phone or our watches. So I suppose 5G is bringing these futuristic concepts that were previously only seen in sci-fi and action movies to life today. But what is 5G and these new concepts and buzzwords that come with the 5th generation of wireless technologies? Today, I want to take everybody through a little adventure as to what 5G is and what some of these concepts mean. As Seamus said, my name is Sharon Keane, and I want to thank everybody for being here today. I'm the Training and Development Manager in Zinworks, and I joined Zinworks in 2018, primarily working on the telecoms domain. Over the last 4 years, I've had many roles. They're mostly all listed there, from Java developer, now currently the Training and Development Manager. I've been so lucky in these roles to work with in many areas of telco, I suppose, as well as I got little dips into the telco or into the financial area as well. But in the majority of these roles, I've worked on telco projects, including network slice orchestration for the new use cases around 5G and IoT. And we'll have a quick look at network slicing later in the presentation, as well as deploying, testing, and terminating virtual and containerized network functions, which we'll also have a quick look at. So before we dive into 5G, I want to have a quick look through the history of the previous generations and how each one was a stepping stone to where we are today in this connected world. So the first generation of wireless networks opened up the wireless doors to everybody. Before this, you had to be at home, you had to be by your phone, and so did the person you were trying to ring, so you could make a phone call. 1G used analog signals to transfer information. Information was limited to voice, and 1G used very low frequency bands, which gave high coverage, high latency, and high battery consumption, which 2 out of the 3 of those aren't great. So when there was long delays in transmission, when there is long delays in transmission, this is referred to as high network latency. and long network delays create bottlenecks in the communication, and it decreases the overall communication bandwidth, leading to low voice quality and dropped calls. If we quickly spin on to 2G, so 2G was one of the biggest advancements at its time. It moved everything from the analog voice over to digital modulation, which then obviously introduced the transfer of data other than voice. And we've seen the introduction of SMS messages. So 2G became a sweeping success with this introduction. Funnily enough, 2G came in 3 different steps or 3 different standards. So the first 2G GSM, which used time division multiplexing and code division multiplexing, and it brought with it the digital voice. We then seen the 2.5 GPRS, which hopefully most people have seen on their phones, the GPRS little logo coming up. Don't get much data transfer with it, but it used package switching so that the data packages could be sent in parallel to the destination. And finally, 2.75G, which was Edge, which came in 2003, and that brought actually multimedia messaging. Onwards from there, we had the 3rd generation of mobile networks aimed at increasing the network speed and the bandwidth, I suppose, with the introduction of wideband code division multiplexing and package switching over 3 of the mid-range frequency bands. This allowed for such greater bandwidth that we see in video calls, mobile internet, and streaming services come online. And it also changed that, I suppose, on the mobile operator side, that you could now pay on the data you transferred as opposed to the time you were using the line, or the non-line as it is, I suppose. For the 4th generation of wireless technology, this is LTE. It was released in 2009, and it supports an even wider range of those mid-band frequencies, wider than the 3G frequencies. It also used IP package switching, which made large data transmission possible with low latency. And 4G LTE, I suppose, is still the main standard that we're using today. Having the high speeds and the low latency of LTE, it brought in such use cases as IP phone, voice over IP, 3G television support, video conferencing, and online gaming, as well as cloud computing. So with these higher speeds that we've seen of LTE, we see new cases being imagined, and where was the end? I suppose LTE couldn't support what was being imagined anymore, and we needed to move on and imagine something new. So this is the birth of 5G. So what is 5G? 5G wireless devices in a cell are connected to the internet and the phone through radio waves, through the local antennas in the cell's base station. So that's just a little bit of background, because everything will build on this. And the new network, 5G new radio, will have greater bandwidth and greater download speeds. But 5G is not just the increase in bandwidth from the previous releases of the wireless network, but rather the fundamental change to the network's infrastructure to support the 5G radio access technology, to support those future radio access networks in an access agnostic way in a single network. And now that's a mouthful, but it's to help, I suppose, cope with this massive traffic explosion that we're going to talk about when we look at IoT, to incorporate future emerging services that may or may not already be envisioned, also to provide cost-efficient infrastructure, and we'll see some of how that's happening later on, and to expand the geographical reach of 5G over the 4G network. So just a quick little animation to visualize the difference in the speeds. So I suppose the biggest difference we'll see here between 3G and 4G, and then 4G and 5G. So we do see that there is some massive speed differences there. So if we look at the 3 distinct categories that 5G is categorized into, you have enhanced mobile broadband, you have the massive connectivity or massive IoT, and you have the ultra reliable low latency communications. The enhanced mobile broadband provides these significantly faster data speeds that we hear about when we talk about 5G. It's approximately going to be 10-fold higher than 4G LTE. Greater capacity allows the users to experience higher speeds, higher quality, better multimedia services, and we'll see more use of virtual reality, augmented reality, 4K and 8K ultra high definition videos, anytime, any place, because it will be mobile on your devices. New application opportunities will include fixed wireless internet access for homes and outdoor broadcasting applications without the need for broadcast fans, because it will be the wireless transmission, and greater connectivity for people on the move. So to imagine a use case where enhanced mobile broadband might be used is, imagine a sold out stadium and you're stuck up the back and there is the All-Ireland hurling final on. Well, for me, I'm blind as a bat, and if I'm up the back, I can't see where the slitter is going. So with the use of augmented reality, virtual reality, the stadium will be surrounded with cameras, and all those cameras will be feeding back the action that's happening on the pitch back to a server. The server will be stitching all those videos together to create an immersive experience, and then any of the subscribers can have that on their device, be it something they wear on their head or on their phone. So you get that feeling of that front row action no matter where you're sitting, even if you could be in the local area outside the stadium. And this is one of the main use cases of enhanced mobile broadband. If we move on to the massive connectivity communications, this is to support the connections and communications among the massive amounts of Internet of Things devices. This involves connecting billions of devices without human interaction and at a scale that's never been seen before. So I suppose they're looking at having millions of devices in a kilometre square over at the moment where you might have a couple of hundred, maybe 1,000. So this is potentially going to be revolutionizing the modern industrial processes and applications, and that includes agricultural, manufacturing, and business communications. So the one main example or use case here would be you have a massive crop farm, and maybe you're in a really hot climate, and every day you have to go out and drive your acres and acres of land, make sure all your crops are okay, water them, check that if they need anything. So a smart farm can have soil sensors that will feed back the pH and the nutrient values of the soil, can treat them appropriately and early, and then you can also get information around crop rotation. You can have drones that can fly over and dispense the seeds, the water, or even pesticides that will help prevent infections. You can have robotics in your smart agricultural solution to help storage and the processing in your warehouse, as well as other agricultural advancements, I suppose, like the livestock tracking and geofencing. All this data can be gathered, transformed, and consolidated to show trends, alerts, and predictions, which can all be controlled from one single device in your home. And this is where the massive connectivity comes in. And finally, then we have the ultra reliable, low latency communication. So there's a lot of mouthfuls here in some of these. But this is also referred to as critical IoT. And this is to enable those delay sensitive and mission critical services, which require very, very minimum delays. So less than a millisecond in delay. The mission critical use cases include real-time remote control of devices such as medical robotics for remote surgeries, vehicle to vehicle and vehicle to everything communication for safety systems, autonomous driving, and safer transport networks. So again, if we take the example of something like the self-driving car, and Ken Power did have a great talk on this morning, but when you add 5G to the already enhancements in the car through software and machine learning, if you add 5G into that, you have this higher coverage, higher bandwidth, and lower latencies of the ultra reliable low latency category. This allows the cars to communicate with each other, but also with traffic lights and the infrastructure of the cities and the environment around it in real time. And it uses cameras, sensors, LiDAR, radar, and in and on the car and in the environment. So this massive exchange of information, the processing of data in real time, will allow the vehicle to understand its surroundings So this means that the car won't just drive from A to B. I'm sitting at home, I say I want to go to work, and it drives the same route every day. But it can make decisions on the environment around it to make route updates to avoid traffic delays. Maybe there's a congested area, can also avoid collisions. And it's that low latency in the communication that is key for reducing those collisions and possibly saving lives. So one of the big things that's driving 5G is virtualization. This is one of the biggest game changers. Virtualization is the process of replacing hardware-based network functions with software-based ones to better optimize the network while increasing efficiency, flexibility, and the capacity of the infrastructure. So by this enables the mobile network operators then to handle the dynamic and challenging use cases of 5G. But virtualization doesn't stop there. Radio access network virtualization is the key architectural component of 5G, and it provides more flexibility and scalability for the operators. And spectral virtualization allows the available spectrum to be utilized more efficiently by multiple providers to share. It allows multiple network providers to share the same spectrum. But virtualization is further enhanced with containerization, which is the packaging together of the software code and all its necessary components like libraries, frameworks, and any other dependencies, so that they are isolated in their own containers. This removes the dependency on the underlying infrastructure and allows mobile operators to be more flexible with their hardware, as well as harnessing the cloud, both public and private. The 5G new radio is the set of standards developed for 5G to meet the outlined requirements in the IMT 2020 specifications. So the new radio makes the wireless broadband performance match, or hopes to match, wireless fixed wired fiber. But it should have significantly lower costs than the wired fiber. So an important goal of the 5G new radio is to support the growth of the wireless communication by enhancing that spectrum efficiency for mobile broadband, including the ability to operate in any frequency band, low, mid, and high. The new radio will support the transmissions of extremely low latency requirements, which is important for those critical IoT cases. And the 5G new radio has broken apart the monolithic evolved packet core that we see in 4G, and it has implemented each function so that it can run independently from each other. The new virtualized network functions can also be run on common off-the-shelf server hardware. This allows the 5G core to become decentralized and the 5G core functions to be co-located with the applications in the edge data centers. And this shortens the communication paths and therefore improves the end-to-end latency. So if we have a look at that, the service-based architecture, the 5G network was designed from the ground up, and the network functions are virtualized and split up into services. So the end user has a smartphone, and this connects to the 5G network radio network over the 5G core and further the data network, so it gets out onto the internet. The access and mobility function, which is right here, acts as the single point of entry for all of the connections. And then the user plane function, UPF, transports the IP data then between the end user and the external network. The other services include the authentication server, which allows for the access and mobility manager to authenticate the device, and allows it to access the services then that it's subscribed to on the 5G core network. Other functions include the policy control, so it applies policies and decisions and accesses subscription information, and this governs the behavior of the network, as well as managing individual user sessions with the session management function. The functions here are not standalone, so they're not individual boxes. They're software processes that are running on commercial off-the-shelf servers. Because these processes are software, we can scale up and scale down the capacity much easier and much more straightforward. So if we take the example of the access management function here, if we want to scale that up, for example, at the stadium, we know that we're going to go from an average of 10,000 people across the whole year to 3 hours where it's 180 people. We're going to need to scale this up. Well, if this is a traditional AMF deployed as a piece of hardware, then that's actually going to take several weeks, even months, to get that piece of hardware up, running, configured. But with a virtualized AMF, this scale up can happen in a matter of minutes. 5G differs from the previous wireless standards due to the massive availability of spectrum, capable of using many more types of frequency at the same time. So the massive spectrum is divided into 3 areas: the low, the mid, and the high band. The low band spectrum is any spectrum lower than 1 gigahertz. And this is the spectrum that the early networks were using. They were all deployed at the low band. Using low band, the mobile operators can serve thousands of customers within hundreds of square miles with just 1 tower. The low band spectrum will make that possible for mobile operators to use a wide coverage. Then the spectrum from 1 to 6 gigahertz is that mid-range band. And this spectrum is considered ideal for 5G because it can carry enough data and can travel significant distance. So a real world, I suppose, example of where this is happening is Sprint in the US is currently operating a live 5G network within the mid-band range in 9 cities: in Phoenix, New York, Washington, Los Angeles, Atlanta, Houston, Dallas, and Chicago and Kansas. And these are in the 2.5 gigahertz spectrum, covering approximately 16 million people in those 9 cities. And then you have the high band spectrum. This is over 24, 25 gigahertz, possibly moving into the 30 gigahertz. And this is where we have the millimeter waves. So the millimeter waves go from where the wavelength is between 10 millimeters and 1 millimeter, which is approximately 30 to 300 gigahertz. The 5G millimeter waves is providing access to massive bandwidth and capacity. The available frequency above 24, in this available frequency above 24 gigahertz. The millimeter waves offer higher speeds over shorter distance, and the bands, but the band has an issue traveling through objects. So I suppose because we're moving closer towards those smaller waves, they find it harder to get through objects. The higher bands provide huge amounts of capacity across large geographical areas. So where the millimeter waves make it key is in those density zones or in smart factories. Beamforming then is the next technique that will be used in 5G networks, and it focuses on the wireless signal. So the wireless radio frequency in the 5G new radio is beamed towards the specific receiving device, rather than having the signal spread in all directions like in 4G, so the broadcast. 5G will beam the signal directly to the device. 5G will introduce this beamforming, which will create more reliable connectivity by allowing a transmitter to focus its transmission in a specific direction towards the mobile device, the vehicle, or the IoT device. The more radiating elements that make up the antenna, the narrower the beam. But because of the narrow beams, you'll also see that there'll be higher security. The result of the direct connection is faster and more reliable than what it would be without the beamforming. And it delivers a higher signal quality to the receiver, which means the faster information transfer with fewer errors, without having to boost the power of the broadcast. Beamforming will typically improve the medium to long range performance. Beamforming will also work with massive MIMO, in which large numbers of antennas at 5G base stations direct beams towards the user's device both horizontally and vertically in order to improve the throughput and efficiency. So to move on to a little bit more on the massive MIMO, massive multiple input, multiple output. This expands across the legacy of multiple input, multiple output we've seen in 4G. So by adding a much higher number of antennas to the base station, this massive number of antennas will focus the energy and bring drastic improvements in the throughput and efficiency. So by using hundreds and thousands of antennas attached to base stations to improve this spectral efficiency and throughput. There are two techniques that are used here in the transmission of data through multiple antennas. And this is spatial multiplexing and space-time block coding. So for me, the one that makes the most sense is the spatial multiplexing. So spatial diversity is one of the fundamental benefits here of the MIMO technology. It aims at improving the reliability of the system by sending the same data across different spatial paths. The spatial multiplexing allows for multiple messages to be transmitted simultaneously without interfering with one another, and they are separated in space. To better visualize this, I suppose, you imagine a base station communicating with a mobile phone through a pipe. There's only so much data you can get through there. But if there's multiple antennas on the base station and multiple antennas on the mobile device, then you can create multiple different paths or pipelines to that device from the base station, which obviously can drastically improve the amount of data that can flow. When we look at the space-time block coding, the data is transmitted at time instance 1, and then later copies of the same data are retransmitted at time block 2 and time block 3. Using this concept, errors can be minimized drastically, but this is at the expense of redundant data transmission over the network. Massive MIMO offers high spectral efficiency due to the large multiplexing gains, high energy efficiency due to the concentrated energy, high reliability due to the large diversity gains, and then it can be developed using low power and inexpensive components. So this enables large reductions in the latency on the air interface. I suppose finally we'll have a quick look at the network slicing. This is the method of creating multiple unique logical and virtualized networks over a common physical network infrastructure. This allows the network operator to split the physical network resources into multiple logical slices and lease these slices out to interested party. So each slice is isolated end-to-end network. So they're sliced vertically, but they're shared. To achieve this sliced network, we must transform it into a set of logical networks on top of the shared infrastructure. Each logical network is designed to serve a defined business purpose. So for example, if we go back to our self-driving car, a network slice that allows the mobile operator to create a specific slice that will be dedicated to self-driving car network. This network is categorized as critical IoT under the ultra-reliable low-latency communication, and therefore the latency needs to be less than 1 millisecond delay. This and many other configurations will be fed into the network description so that it can maintain its SLAs. These networks will be closely monitored and using many techniques like machine learning, artificial intelligence. Network trends can be monitored and predicted. And these networks then can be scaled up and scaled down either by the network administrator or on hitting specific benchmarks. And this is where network slicing is one of the key parts of 5G networks. So 5G is just faster downloading of movies to your phone, higher quality videos, right? Hopefully not. 5G is a redefinition of the wireless communication standards and the technologies behind it. We looked at the 5G use cases and the distinct categories, so the enhanced mobile broadbands, the massive connectivity, and the ultra-reliable low latency. And then we quickly looked at the main concepts behind those that are driving the 5G revolution. So quick around the spectral efficiency and the millimeter waves, the massive MIMO, beamforming, and network slicing, as well as a quick view of the architectural changes using virtualization and containerization. I am definitely looking forward to the new opportunities that are going to be opened through many of these revolutionized industries, but also what doors will be opened in new innovations. and what 5G will bring over the next few years, and how much of this sci-fi will come to life. That's all I have today. Thanks a million for your attention. Is there any questions?
Thanks. And for showing us what 5G really is. I think that's kind of interesting. One of the things that I read recently was like one of the tech journalists gone, well, what's really the benefit for the consumers at the moment of 5G, because it's not that rolled out all that much across our networks in Ireland just yet. So are we actually seeing the benefit? But I think hopefully what you've shown us is that the best is kind of yet to come when it comes to that. Would that be fair?
Yeah, exactly. And I suppose we can look at some of the use cases there now. So I suppose Kansas City will be one of the first big smart cities at the moment. And when you read about what's happening there, it's really amazing. So they have the whole city visualized in an app. So if you're a pedestrian or if you're driving your car, you can see where the congestion is, where the hotspots are, and you can use that augmented layer as well. So you can, I'm not sure if you've seen those little videos where you have that augmented reality layer over your camera, and you can just look where is the local cafe, and it literally just pinpointed for you on the map. It'll open your street view, and you're looking down, and it'll tell you where to go exactly. So I suppose some of these advancements are going to be amazing. And then we see where China has done some of these remote surgeries, and they've actually done some human trials, which is amazing, and it's new. And the doctor is, hundreds of miles away using a robotic arm and performing these surgeries. And I suppose it just means that then healthcare becomes a lot more accessible to people.
Absolutely, yeah. There was one thing I was just interested in when you talk about the low latency part of it and the network slicing, and you gave the example of the autonomous vehicles and maybe setting up that dedicated link for things like autonomous vehicles. And I was listening to Bobby Healy, the guy who runs Mana Drones, the drone delivery company, and he was kind of explaining how they use 2 different SIM cards in every drone. Basically, one is obviously fault tolerant for the other, for all that things like collision detection, etc. For technologies like that, are they fundamentally relying on 5G, or can they get away with what's there today with 4G?
So I suppose with the autonomous cars, I don't know if you got the 11 a.m. talk that we had on today, but technically something like the autonomous cars aren't necessarily depending on the 5G network. But I suppose when we look at the enhancements that, like, a car can drive from A to B with some sensors, and a sensor can go, yeah, there's something in front of you, stop. And that's realistically what we're going to need for self-driving cars. But when you put in multiple sensors that are going to be reading more than just what's directly in front of you, and you have traffic lights coming up where you want to avoid congestion, or there's been a collision, the road's closed, and you have a self-driving car, you don't want to end up at a traffic light or at a roadblock where the road's closed, and now you have to go try and find an alternate route yourself and try and figure that out. So when you bring in the 5G network, the car is going to be gathering so much information and processing so much information at such a speed that it will be able to make these decisions itself with the data that is being provided by its environment.
Yeah, makes perfect sense. If they can solve Galway's traffic problems for those living in Galway, that would be
lovely, wouldn't it?
But I don't know if that's going to happen anytime soon. That's a whole different discussion. I have one last question, and again, for anyone there, would encourage you just to put your questions in Q&A. I'm happy to put them to Sharon for you. I had one kind of last question. I was kind of interested in that kind of high bandwidth, those really high speeds where the waves are obviously that much smaller, and you talked about the difficulty in getting through buildings and that kind of stuff. Does that mean that those use cases are going to be kind of limited to like that stadium use case or some of those types of use cases?
Yeah, so I suppose the biggest thing with 5G is that it'll be able to use each of those bands for each use case that it needs. Yep. So for example, those millimeter waves where it's really high bandwidth but short distances, you're going to see those in real dense cities. You're going to see them in factories. So you'll see where you have a smart factory, and this is where it'll be amazing. You have robots flying over and back, and cranes and production lines going, and you're there, you have maybe you're a few guys going around monitoring. You're not going to want a robot to run straight into that guy or a crane to land something down them. So you're going to need that real high bandwidth there and those high speeds and that high data transfer there. So it will be used for those use cases. Yeah.
Very good. Very good. So Daniel just asked there, or sorry, David asks, hi, many thanks for the presentation. What security features are included natively in 5G? So is there anything that's specifically native to 5G in relation to security?
Well, I suppose one of the big things with, I think I kind of half mentioned it, is with the beamforming. So I suppose if you're thinking about 4G and all the previous generations of wireless transfer of data, you have this big broadcast spectrum where your information is just broadcasted out and it hopes that you're going to pick it up. Your device is registered to pick this up. But obviously that isn't necessarily always the best. So one of the big things natively, I suppose, with 5G is the beamforming. So with that transmission being a lot smaller and being directed at your device and where you are, that's going to definitely be one of those native security features that you're going to have in 5G. I suppose with the containerization and the cloud as well, there will be a lot of security around. I suppose it's kind of a twofold thing. Some people say there isn't as much security in the cloud, but you know, you have a lot of that redundancy backups, you have a lot of recovery there as well. I suppose it's not fully security, but you have that secure kind of feeling, I suppose, a bit more about the 5G as well.
Yeah, the fact that it's extensible, you know, as you can scale it up as a soft piece of software.
Yeah.
Fantastic. Thanks a million, Sharon. Thanks for bringing us through this. I think we've all heard the big hype about it, but it's great to get a much more detailed understanding of what's coming. As you said at the end of your presentation there, it's going to be interesting to see how far towards the science fiction movies we get to, but this helped bring us a lot towards this, so it's been an exciting journey. Again, thank you so much for taking the time to join us on the AtlanTec Festival today. Just for everyone else, just a reminder, we're kind of live all week. As I said, it's all virtual events today, tomorrow. We've got an in-person event on Wednesday morning at NUIG, talking about the future of software development. And again, we're online again on Thursday as well. So make sure you look out, go to AtlanTec.ie and register for the rest of the events. Sharon, thanks again so much, and take care. Talk to you soon.
Bye, guys.